Oh, y'all, welcome to Home Away from Home. Been here long enough that it's home. Wow. As you can see, I ain't making it to class on Tuesday. I'm doing this one on Monday. There's no way I'm making it to class on Tuesday. So, you guys paid your tuition. You are going to get your money's worth. All right. So let me start with the homework assignments from lecture 6, okay? And the first question is really straightforward. Come on now. Not that one. Ignore that one. This one. Come on. There it is. When are events independent and when are events dependent? And we've talked about this. We did it, in fact, just last Thursday. We had the whole conversation about, imagine you've got a deck of 52 playing cards, and I said, what's the probability of drawing a queen? And you say, well, there's 4 queens, there's 52 cards, 4 over 52. And then I said, okay, what if I then draw a card and then put it back in the deck, shuffle the deck, and then ask again, what's the probability of a queen? And you're like, well, 4 over 52, all right? There's still 4 queens and there's 52 cards. Well, these events are independent because the outcome from the first time I took a card out is absolutely does not affect the second time. If I was to do the same thing, but instead I was to say, here's 52 cards, which probably is drawing a queen, 4 out of 52, lovely. I draw a card and it's something else. So I take it, toss it. Now I'm holding this new deck with 51 cards and say, what's the probability of getting a queen? You go, oh, now it's 4 over 51. Okay? And so clearly what happens is that in a situation with dependent events, the probability is dependent upon what has already occurred. Okay? So it's a simple enough distinction, which I hopefully we've got. 6.2 is hopefully nothing but an absolute and utter review for us. This is what we did all of last week. It's going to be the next question. It's going to be not review, but that's okay. This one is completely review. And so the mean of a population of raw scores is 50 with a standard deviation of 18. What is the probability of randomly selecting a sample of 40 scores with a mean below 46? Because the question is talking about a sample of scores, we know that we will not be using the distribution of raw scores, but instead the sampling distribution of means. I knew you knew that. Sampling distribution of means. And the sampling distribution of means will have a mu of, that's right, exactly the same as the mu from the original raw scores. So if the raw scores had a mu of 50, the sampling distribution of means also has a mu of 50. What about the standard deviation of this distribution of sample means? Everybody remember that one? Because remember, the sigma from the raw scores will not equal the sigma in this distribution of sample means. Instead, this distribution of sample means will have a sigma, which is actually now going to be called standard error, right? Sigma sub x bar, and it will be defined as the original sigma divided by the square root of n, or in this case, the 18 that came from the population of raw scores divided by the sample size of 40, square root of that, they got 2.85. Okay? Wow, it almost looks like a minus sign there. Oh, I guess it's an equal sign. Equals 2.85. So we see on that top graph there, I've simply drawn out, a mu of 50, and so plus 1 standard error, in this case, 52.85, minus 1 standard error, 47.15, and we got the z-scores labeled along the bottom. So now, in this new distribution of sample means, what's going on with that sample mean of 46? So you see in the bottom picture, I lay out that 46 as a sample mean, and your job is to figure out how strange is this sample. We know that if we have some raw scores, or in this case, a sample mean, then in order to say anything about probability, the next thing we have to do is go through the z-score, right? Pretty straightforward. So using the z-score formula that we've learned quite extensively, we take the mean of the sample, in other words, what is it there? 46 is what we're looking for, minus the mu of the original distribution of scores, which is 50 right up there, and divided by this standard error of the mean, which we just calculated at 2.85, and get a z-score of negative 1.4. So now, looking this up in your z-score chart. Yes, pull out your z-score chart and actually look on it, please. Thank you very much. So now, in order to look this up, what we're going to look up is, remember, down the left side until you get to 1.4, and then you'll go over no columns, right? You'll take the very first number next to 1.4 because it's 1.40 in this case. When we look it up, remember what we're going to find in this chart is the distance between the score and the mean. However, this question is not asking for the distance between the score and the mean. This question is asking for how big is the tail, or what is the probability of randomly sampling a score this low, right? It's asking what's the probability of getting anything to the left of this point. So if we look up 1.4 in the z-score chart, it should say 0.4192 if I'm correct, right? 0.4192. And so we know that 0.4192 is an interesting number, but not our answer. Instead, we say the entire left side of the z-score distribution equals 0.50. If the area we don't want is 0.4192, the difference is 0.0808. Okay? So probability is 0.0808. Again, hopefully that is just review, I hope. So let's move on to a new one. Not that one, because that's an old one, isn't it? That one. Okay. On a standard test of motor coordination, a sports psychologist found that the population of average bowlers had a mean of 24. Okay, the original mu is 24. The original sigma is 6. She tested a random sample of 30 bowlers, so n equals 30. She tested a random sample of 30 bowlers at Fred's bowling alley and found a sample mean of 26. A second random sample of 30 bowlers from Ethel's bowling alley had a mean of 18. Okay, first off, I know you're still new at this, but you are being asked two distinctly different questions. Do not mix these together. Don't try to, no. First we'll do Fred, then we'll do Ethel. We will not mix these up. So we'll start with one and then the other. So now here's the part of this problem that's going to be new for us. Using the criterion of p equals 0.05 and both tails of the sampling distribution, okay, let's take a look at that before we move any further. So what it's saying is, when it said probability equals 0.05 or probability equals 5%, right? These are the same statements. And then it says two tails. That's an indication that you're supposed to take that 5% and split it into two parts. So as we can see on this slide, I've drawn these little arrows pointing to the left, pointing to the right, both of which at 2.5%. And so what it's looking for there is what are the z-scores that are going to cut off that 2.5%, okay? Because 2.5 plus 2.5 equals 5, okay? So which z-scores will hit that spot? And so, of course, what we're going to have to do is that part that some of you don't like. We're going to have to go into the z-score chart, and we're going to have to find the z-scores that correspond to those percentages. But again, that silly z-score chart just doesn't have that piece of information, does it? The z-score chart always tells us the distance between the score and the mean. But we want to know the distance between the score and everything to the right or everything to the left. Okay? And so we're going to have to think about this a little bit and say, okay, well, first off, I guess I want to take a very short step back. We know that if we find the number that sets off the top 2.5%, it will be the exact same number that sets off the bottom 2.5%, okay, because of the mirror image nature of this curve. So once we have one, the other one is just a negative, right? It's just the opposite. So if we're looking for the top 2.5%, that means that the distance between the mean and the point I'm interested in is 0.475 or 47.5%, right? 47.5% plus 2.5% equals 50%. And so in the z-score chart, we need to find 0.475. Okay? So let's take a quick look at this thing before I step back to the problem again. Now, we look in this chart and we're like, okay, I need to find 0.75, the distance between the score and the mean, 0.47. 475, I know the right answer, I've already got the answer, but anyway, what we find is, ooh, I got it exactly this time. If you remember during class and every example we've had, we've never hit the exact answer. We always had to estimate, we always had to guess. Well, look at that, we're lucky. We've got an exact 0.475. In this 0.475, it corresponds to a row of 1.9 and a column of 0.06. Therefore, the scores that separate the top and bottom 2.5% are positive 1.96 and negative 1.96. Now, these are going to be important numbers coming up in the next chapter or two, and they'll start to become familiar, okay? So with probability 0.05, two tails is plus and minus 1.96, okay? These are familiar. Okay, going back to the original question because we got sidetracked there. So now, second round, using this criterion of probability equals 0.05 and two tails of the distribution, what should she conclude about each sample's representativeness? All right, this is going to be an interesting story. So we'll start with this two separate questions. Huh? Here we've got Fred's bowling alley. Okay, we're going to start. In fact, you know what? Stepping back, I'm going to go back again. I know, I'm sorry. Going back. Let's go back here. And let's remind our, no, in fact, it's not even there, so I won't say that. Ha, going back to Fred. So remember, this distribution of sample means will have a mu equal to the original sample mean. So look at what I got drawn there. I got a 24 in the center, and a 20. Just remind you, where is it? 24, there it is. Had a mean score of 24. So it's centered at 24. But the standard deviation of this distribution of sample means will not be the original sigma. Remember, the original sigma is 6, got it? A standard deviation of 6. So it will not be 6. Instead, it will be defined by sigma sub x bar. The original 6 divided by the square root of the sample size equals 1.1. And so we see in the image that I've drawn, it's centered at that 24, the mu, and one standard deviation up, 25.1, one standard deviation down, 22.9. And now I've laid out my little z-scores of plus and minus 1.96 that we've decided are the important numbers. And let's calculate the z-score for Fred's bowling alley. Okay, Fred's bowling alley, going back again to grab the number. Fred's bowling alley had a sample mean of 26. Okay? And so the sample mean of 26 minus the population mean of 24 divided by sigma sub x bar of 1.1 equals positive 1.82. Okay? So take a look at the arrow and where's the arrow pointing, and you can see what's happening is that positive 1.82, it's a relatively large z-score. Okay? There's no doubt it's kind of a big number. But we see that that 1.82 does not fall in those outside regions. In fact, those two regions right there, the 2.5 to the left and 2.5 to the right, are going to have a special name moving forward. We haven't come up with it yet, but here's a little preview. They're going to be called regions of rejection. And so it turns out that that 1.82 does not, in fact, fall into a region of rejection. Okay? It falls into a region of literally non-rejection. Okay? So if the areas beyond 2.5% equals region of rejection, the other areas equals non-rejection. And so look at that. I'm going to look at this, and here's my statement. So positive 1.82 is not in a tail beyond plus or minus 1.96. Therefore, we're going to conclude at Fred's bowling alley, these probably are just average bowlers. Okay, there's nothing really special about Fred's bowling alley. Okay, well, let's look at Ethel. Now, it's the same basic question, right? Same basic question here. And so we're using the same standard error because remember at Fred's Alley there was a sample size of 30, at Ethel's Alley there's a sample size of 30. So it's the same sampling distribution here, exactly the same as Fred's Alley. So when we calculate the z-score, we've got the mean, the sample mean, okay, going back. Ethel's bowling alley sample mean is 18. Okay? So put in the 18. So sample mean of 18 minus population of raw scores mean of 24 divided by the standard error of 1.1 to get a negative 5.45. And look at my arrow. Holy moly. Is that negative 5.45 in the region of rejection? Heck yes. That is way out in the region of rejection. And again, I've sort of been talking about this. I've talked about what equals a freaky sample or a really strange situation. And this is it. This 1.96 z-score, or in this case negative, has become our definition of a strange score. And so all of a sudden, if the z-score that I obtain, negative 5.45, is in one of these regions of rejection, then what we're going to say, just as a general statement first, the bowlers at Ethel's bowling alley are probably not representative of all bowlers. There's something strange about Ethel's bowling alley. In other words, the bowlers in Fred's bowling alley may just be average normal bowlers. Okay? The bowlers in Ethel's bowling alley, there's something freakishly strange about them. Okay? These dudes are not doing well. Okay? So we'll expand more on this in lecture 7, which I'll record once I've taken a break. Okay? So I will see you guys in the next lecture in a handful of minutes.